All right, guys, welcome back. We're doing part 2 of energy when it comes to rotational motion. So let's get to this. A solid sphere is rolling without slipping along a horizontal surface with the speed of 5.5 meters per second. When it says without slipping, that means there's friction because it's going to slip if there's friction or if there isn't friction. But if there is friction, it's not going to slip, okay? With a speed of 5.5 meters per second when it starts up the ramp. Okay, so it has initial velocity 5.5 meters per second. The ramp makes an angle of 25 degrees, the horizontal. What is the speed of the sphere after it has rolled 3 meters up the ramp? Okay, after it has rolled 3 meters up the ramp, measure along the surface of the ramp. Okay, so let's figure this out. Again, we want to do mechanical energy initial is equal to mechanical energy final. Okay? So let's try to figure this out. At the beginning, what we have is we have two things. We have kinetic energy rotational because it's rotating. And we also have kinetic energy translational because it's also moving linearly. Okay, so we have two things. As it goes up, there's also going to be, as it goes up 3 meters, there's going to be gravitational potential energy. And what is the speed? So we're going to figure out also how fast it's moving. So it's still going to be rotating and it's still moving translationally. Okay? So that's how we should be setting this up. All right. So now let's figure out for a few things. First of all, if it goes up 3 meters. So 3 meters, right? Let's just figure out how high that is. Okay? What's the height that reaches? Okay, so I'm going to do, in order to find this, I'm going to use sine. Okay, so I'm going to do sine of 25 is equal to opposite h over 3. And then now I get h is equal to 3 times sine of 25, which gives me 1.27. Okay, so this gives me a height of 1.27 meters. All right, so now let's figure this out. So we have rotationally one half, and then the inertia, which is 2/5 m. Is m given to us? M is not given to us. Okay, r squared is r given to us? No, r is not given to us. R squared, and then we have omega squared. Okay, omega squared plus 1/2 m, again not given to us. V squared. So it is given to us initially. This is going to be 5.5 squared. Okay, I'm going to put that in parentheses. And then now this is going to equal m, not given to us, gravity, 10, height, 1.27, plus 1/2 m v squared, that's what we're looking for, plus 1/2, and again, this is rotating, so 2/5 mr squared omega squared. One thing we should notice right away, the m's cancel out, okay? M's cancel out because m is in every single part of this equation, so the m's cancel out. The next thing we should notice is this. We have two unknown variables, the omega and the v. So this is omega final. This is v final, this is omega final. So what I should do is I should change this omega. As we know from before, omega times r equals v. So that means omega is equal to v over r. So I'm going to change this omega, and I'm going to change this to be v squared over r squared. V squared over r squared. What happens now is these r's cancel out. And we know what this v is. We know how fast it's moving. It's 5.5. So I'm going to change that to be 5.5. 5.5. All right, now let's do the same thing over here. We're going to change this omega final squared to be equal to v final squared over r squared. Again, this r cancels out. All right, now let's do some algebra here. Or algebra, math. 1/2 times 2 divided by 5 times 5.5 squared. What we get is 6.05 plus 5.5 squared times 0.5, 15.13 is equal to 12.7 plus 1/2 VF squared plus 2/10 VF squared. Okay, now let's put all the whole numbers all the way to the other side. So we have 6.05 plus 15.13 minus 12.7. We get 8.48. And it's going to be equal to 5 over 10. So it's going to be 7/10 VF squared. Now I'm going to put that multiply by 10, divide by 7, and then square root that. And we now get V final is equal, whoopsies, V final is equal to 3.48 meters per second. Might be a little bit different if you use 9.8, but that's what you should get. Okay, so when it rolls over here, it's going to be moving linearly 3.48 meters per second. Okay, big tricks right here is knowing this and just writing everything down at the beginning. Okay, writing down all the different energies that's happening before it goes up the hill and at that point of 3 meters up the ramp. Okay, all right. Let's try another one, similar problem. A solid uniform sphere of mass 2 kilograms and radius 1.7 meters rolls from rest without slipping down inclined plane of height 7 meters. Okay, this has a height of 7 meters. Okay, what is the angular velocity of the sphere at the bottom of the inclined plane? Okay, we want to find what is the angular velocity, so final angular velocity. Okay, so let's figure this out. Again, let's do mechanical energy initial is equal to mechanical energy final. At the beginning, it's at rest, so there's only going to be gravitational potential energy. Okay, it's not rolling, it's not moving. And then as it goes to the very bottom, there is no gravitational potential energy. There's only kinetic energy, translational, because it's moving linear, and there's only kinetic energy, rotational, because it's also turning while it's moving. So let's figure this out. So mass, which is 2, gravity, which is 10, height, which is 7, is equal to 1/2 m2 v squared, which we don't know, plus 1/2 they give us the inertia 2/5 m, which they give us 2 r 1.7. They also give us that squared. So that's the I, 2/5 mr squared, and then this is going to be omega squared, which we're looking for. Okay. Now for this one, since this is what we're looking for, omega final. However, we don't know what V is. So again, we want to look at that same equation. We know omega R equals V. But this time we want to substitute V with omega and times R. So I'm going to change this V squared, and I'm going to make this omega times R, which is 1.7. And this is both squared. Okay. All right, so now let's put this into our calculator, try to simplify this best we can. 2 times 10 times 7. We get 140 is equal to 1.7 squared. So this is going to be 2.89 omega squared plus, this is going to be tough, 0.5 times 2 divided by 5 times 2, wait, hold on. 2/5 times 1.7 squared, and it's going to be 1.16 omega squared. And now let's try to simplify. 140 is equal to 1.16 plus 2.89. So this is going to be 4.05 omega squared. So now we do a little bit of algebra and square root that. And we get omega is equal to 5.88 radians per second. Okay? So hopefully you guys are starting to get used to this. There's a lot of algebra here, but hopefully you guys are very comfortable with the algebra by now. All right, let's move on to the next problem. So this is all variables, so this might be a little bit confusing, but I'm sure you guys can do it. From the following diagram, find the translational velocity of the yo-yo. Okay, so we're looking for V10. Use the following variables, R, H, G. If the yo is dropped without being held by the string, would its velocity be more or less? Okay, so let's just do part A. So part A, we have it here at rest, right? Let's just do, again, mechanical energy initial is equal to mechanical energy final. At the beginning, it's at rest. The only thing there is potential energy. After it's rolling, we're going to say that this is the zero line right here. You always want to put the zero line at like the lowest point the object's going to go. So that's the 0 line. So that means there's no gravitational potential energy because at the 0 line. And then, but there's going to be kinetic energy translational because it's moving linearly, and kinetic energy rotational. Okay, so let's see what we got here. So the inertia of a solid cylinder is equal to 1/2 mr squared. Okay, knowing that, let's go. So we have mass times gravity times height is equal to 1/2 mv squared. This v is what we're looking for. This is going to be plus 1/2 I, which is going to be 1/2 mr squared times omega squared. All right, now let's start replacing some of these variables. We have m, which we're fine to have. Oh, well, okay, one thing we should realize right away. M is in every part of this equation. So what that means is m cancels out. Okay, m is in every single part of this equation. So that means m cancels out. Another thing. Okay, now let's start replacing some of these variables. So we have gh. Oh, no, that's going to be the same. 1/2 v squared. That's what we're looking for, v. Plus 1/2. And then r, we should replace it with this capital R. So 1/2 times 1/2, that's going to be 1/4. Let me change this. 1/4 r squared. And since we're not looking for omega, we're looking for v, I'm going to change omega from like our last problem to be v squared over r squared. Okay, and you can see this also, this r cancels out when we do that. So now what we have is gh is equal to 2/4, so 3/4 v squared. So now we could do 4/3 gh equal to, and the square root of this equal to v. Boom. Okay. So those are all variables. Sometimes students have a hard time with that, but don't let it trick you. Just it's the same thing, except you're just using variables instead of numbers. So part B, if the yo-yo is dropped without being held by the string, would its velocity be more or less? So now there's no string here, you just drop it. Would it be more or less? The answer is the velocity would be more. Why would it be more? It's because right now, if it's just dropped, it's no longer going to be rotating. And if it's no longer rotating, that means all of the potential energy at the beginning just turns into one thing, translational kinetic energy. It doesn't waste its energy rotating, so all of it just changes into kinetic energy translational, which means the velocity would be more. Okay? All right, let's move on to the next problem. A light string is wrapped around the outer rim of a hollow cylinder of mass 4.75 kilograms. Okay, mass 4.75 kilograms. Okay, the cylinder is then released from rest. How far must the cylinder fall before its center is moving at 6.66 meters per second? Okay, so this is an interesting cylinder. It's a hollow cylinder like this, so this is the inertia for it. So again, let's try to figure this out. Mechanical energy initial is equal to mechanical energy final. What we have is at the beginning, wrapped around, the cylinder is released from rest. Okay, so all there is gravitational potential energy. It's going to fall, and there's going to be kinetic energy translational, and then there's going to be kinetic energy rotational. Okay, and we're looking for how far must the fallness fall before it. So we're looking for the height, like how much does it have to fall? So we're looking for the height of everything until it goes 6.66. So we're going to do mass, which is 4.75, gravity, which is 10, height, which that's what we're looking for, is equal to 1/2 mass 4.75 v square, or no, v. We want it to be going 6.66 meters per second. So 6.66 squared. Okay, interesting number. Plus 1/2. Okay, so this is going to be a little bit interesting now. So we have this inertia. So 1/2 mass, which is 4.75. R1. So R1 is this inner rim, 20 centimeters. So it's going to be 0.2 plus, 0.2 squared plus 0.35 squared. And yep. So that's the inertia, and then omega squared. But what we're going to do is we're going to change that omega squared. We're going to change it to be v squared over r squared. Okay. And this is where it gets a little bit confusing, because can we just cancel out this these two r's? And the answer is no. Why the answer is no is because we're going to change this velocity here, and we're going to change this to be 6.66, right? But where it's going 6.66 is going to be at the outer rim. So it's going to be going 6.66 here. It's not going to be going 6.66 here. It's going to be a little bit less. So that means the radius we have to use is this 35 centimeter one, not the 20 centimeter one. So this one is going to be divided by 0.35. Okay. So hopefully you guys understood that. That is a bit confusing. All right, but let's try to simplify this as much as we can. So 47.5 h is equal to, let me put this into my calculator, 6.66 squared times 4.75 times 0.5, 105.3 plus, oh, this is going to be hard, 0.5. Well, let me do the one stuff in the parentheses. 0.35 squared plus 0.2 squared, and then times 4.75 times 0.5 times 0.5. Then I get 0.19, and then I'm going to multiply this by 6.66 squared, and then divide it by 0.35 squared. And then I get 69.87. All right, so let's see what we can do here. Okay, so now I'm going to add that plus 105.3. So it's going to be equal to 175.17. And then I'm going to divide this by 47.5. And what do we get? We get a height of 3.69 meters. Boom. Okay, that was probably pretty rough. Okay, pretty rough. But anyway, that's how you do that one. Play it back, of course, if you were confused. And I'm sure after you see it a few times, you'll be fine with it. All right, if you drop the cylinder without any string, how fast would the cylinder be moving when it has fallen the distance in part A? Okay, so part B, it's not rotating, there's no string, so you're just pretty much dropping an object. If you're dropping an object, we're just using the whole linear thing. So mechanical energy initial equals mechanical energy final. So we drop something, it has gravitational potential energy at the beginning, and then there's going to be kinetic energy translation at the end. That's all there is. So mass, 4.75, gravity, 10, height, 3.69, and then it's going to be is equal to 1/2 mass 4.75 v squared. Okay, we can get rid of this 4.75. All right, let's do this. 36.9 times 2 square root 8.59 meters per second. Okay, so it's going to be moving a lot faster because it doesn't have to rotate anymore, so it can move a lot faster. All right, last problem here. Let's try to do this one. A playground merry-go-round has a radius of 2.4 meters. Okay, 2.4 meters, and a moment inertia of 2,100 kilogram meters squared. Okay, 2,100 kilogram meters squared. Okay, about a vertical axis through its center. A child applies an 18 Newton force tangential to the edge of the merry-go-round for 15 seconds. If the merry-go-round is initially at rest, what is its angular speed after 15 seconds? Okay, so let's see what we have here. So we're going to be applying a tangential force of 18 newtons. We're going to be applying it for 15 seconds. It's initially at rest, and that's what we know. So just looking at this, and we also know the radius, 2.4 meters. Looking at this, I feel like, okay, I could probably find the torque. I know the force and the radius. So torque equal to force times radius times sine of theta. The force is 18, radius is 2.4, and we're applying it tangentially, so this is going to be 90, which is going to equal 1. So I can see that the torque is going to be 18 times 2.4, which is going to be 43.2 Newton meter. Okay. Knowing that, I also know torque is equal to inertia times alpha. So I can say 43.2 is equal to inertia 2100 times alpha. And then I can say alpha is equal to, divided by 2100, 0.02 radians per second squared. Okay? But, okay, that's not what the question is asking. This question is asking, what is its angular speed after 15 seconds? So, what we're going to do now is we're going to see what we know with kinematics. So, omega initial is equal to 0. Alpha is equal to 0.02. Time is equal to 15. And we're looking for omega final. Okay? So, now let's see if we can figure this out. Omega final is equal to omega initial plus alpha t. So omega final is equal to 0 plus 0.02 times 15. And then we get omega final is equal to times 15, 0.31. 0.31 radians per second. Okay. So not really anything to do with energy or work. The first one. How much work did the child do on the merry-go-round? Okay, so now we're trying to find how much work that the child did. So at the beginning, there's no energy, but then once it starts moving, now there's kinetic energy. So just know that the amount of work that he did is the change in energy. So change in energy is equal to work. So let's see if we can figure this out. So at the beginning, there's no energy, and then there's an increase of kinetic energy. So this is just it's only kinetic energy, so it's just going to be the work is equal to the change in kinetic energy, which is going to be 1/2 I, which is 2100, omega squared, 0.31 squared. And the initial was just 0, so we don't have to do all those calculations. So we get 0.31 squared times 2100 times 0.5, and we get 100.9 joules. Okay? All right. Part C, what is the average power supplied by the child? Okay, interesting. Power. So remember, power is work divided by time. So we know the work that the child did, 100.9, and we know how long the child was working, 15 seconds. So 100.9 divided by 15, and we get 6.73 watts. All right, guys, that's it for energy. Hope you guys were able to understand everything. And good luck with everything. Thanks for watching.